Okay, so we're looking at the real zeros of a polynomial. This stuff is all based on the fundamental theorem of algebra, and these different theorems associated, or algorithms associated with, are all associated with the fundamental theorem of algebra. So it's a way to help us, at the core here, this is a way to help us to apply methods of factoring, like third degree, fourth degree, and so on. We're really just going to apply this to third and fourth degree just because it's so labor intensive beyond that. So when you get problems on this, I'll ask you to use it on primarily third and fourth degree polynomials. Okay? Division algorithm. Let's define that. The division algorithm says the dividend is equal to the divisor times the quotient plus the remainder. So think about a division problem. Let's take one from arithmetic here, if I have, or even just do this. So if we take, say, 12 divided by 4, let's do one that has a remainder. How about 13 divided by 4 equals, 4 is going to go into 13 3 times, right? 3 times. So it's 3 times is the divisor. We have, let's see, divisor is actually 4. So it goes in 3 times with a remainder of 1. So it's 3 and 1/4 is how we write that as a mixed number. So if I'm writing that as a division algorithm, I think I'm going to show you that next here. No, not yet. So if we write something as in division algorithm format, so if we have 13 divided by 4, we want to write that all out as a division algorithm problem, then what we would do is take the dividend, which is 13, and it equals the divisor, which is 4, times the quotient, which is 3, plus the remainder, which is 1. And so all of this, 4 times 3 plus 1 equals 13. So that's a way to take a basic arithmetic problem and write it in that division algorithm format. Okay, and we're going to do that with polynomials. So you did some long division with polynomials last year, right? A little synthetic division too? Yeah. And so we can write polynomials in that same way. As a matter of fact, probably when he introduced dividing of polynomials to you, probably even started with like a long division problem from 6th grade. I bet he did that because it follows the same format. So it says if r of x, that's the remainder of x, equals 0. So if this is 0 right here, the remainder is 0, then d of x and q of x, here and here, are factors of f of x. All we're saying is that if I change this 13 to a 12, then I would get a whole number 3. In other words, I could write 12 equals 3 times 4 plus 0. If the remainder is 0, then these two numbers are factors. So remainder theorem. If f of x is divided by x minus c, then the remainder is f of c. It's the remainder theorem. It says if f of x, so if f of x is a polynomial, and it's divided by x minus c, so that would be a suggested factor, I guess. It may or may not be a factor because it depends on whether or not the remainder is 0. But if you divide x minus c into f of x, then the remainder is always f of c. That's interesting. That's kind of what's behind the, let's blank on it. For the long division, we call it, who said it? Just the shortcut that you use. What do you call that now? Synthetic division. Yeah, synthetic division. That's what's behind synthetic division. Is if you actually plug in c to the original polynomial, it will tell you if when you go to do long division, it will divide in evenly or not. Okay, so if you get a 0 when you plug it in, that means that that is a factor. And if you don't, then it's not. So that's what's behind synthetic division. Okay. So if we have a polynomial like 2x cubed minus x squared plus 2x minus 3, and we want to go ahead and do some division. It says here, divide the function by each binomial using synthetic division, verify the remainder using the remainder theorem. So let's go ahead and do the long division here. Or put this pen down.
Long division?
Sorry, synthetic division. We're not going to do long division. Sometimes we need to do long division. Long division is more global. It works all the time. We can use, by the way, when can we use synthetic division? You remember? Yes, Jess, you remember? It doesn't have to be factorable. Sometimes we use synthetic to see if it is. We're doing the division to see if we get a remainder of 0. Yeah. Yeah. Or we want to make sure there's no number before the x. You can actually get around that. It's kind of a pain. I usually avoid that. If you had something like 2x minus 1 here, I would probably just use long division. There's a way around that to adjust it. But what we need is a binomial that's a first degree that we're dividing into it. Okay. And so we take this negative 1, or take, the factor is x minus 1, right? So that means we take the opposite of that 1. We put a little box around it. Okay. I think you probably did quite a bit of this last year. Right? It's not a difficult process. You forget? Okay. Well, we'll review it right now. So we take the opposite of this. So whatever would make this factor 0. Okay. Place it down there in the box. And then we take the coefficients from the polynomial with placeholders if necessary and bring them down. So 2, -1, 2, -3. Okay. There's our setup for synthetic division. Then draw a line underneath this here. Bring down the 2. And we do 1 times 2. So 1 times 2 equals 2. And then add those. So 2 plus -1 would be 1. 1 times 1 is 1. 2 times 1 is 2. Left enough room here. Good, I did. So then 1 times 2 is 2. -3 plus 2 is -1. So let me first ask you this. Where? Oh yeah, I need to add. Sorry. I'm doing there. Yeah, 2. Yeah, I don't know why I got the one there. So 3, and then 1 times 3, good. So what does this mean when I get a 0? It's factorable, and what is one factor?
1. X.
Okay, that's a 0. Yeah. So what is the factor? X minus 1, right? So x minus 1 is a factor. 1 is the 0, the polynomial. So when you get a remainder of 0, now what the remainder theorem says is that if f of x is divided by x minus c, then the remainder is f of c. So what this is telling me is that I could quickly check this just by plugging in c, and c, remember, was 1. So let's do that right now in a different color. So f of 1 equals 2 times 1 cubed minus 1 squared plus 2 times 1 minus 3. Can you do the arithmetic on that? What do you get?
1.
Not 1. Not 1. What should we get here if x minus 1 is a factor? Yeah, Jess?
0.
We should get 0. Do you get 0? As long as you're not doing funny arithmetic like I was. Get 0, you should. So that's what the remainder theorem says. You can just plug the number in, and if you get 0, that means x minus that number is a factor. That's a quick way to check it. That's what's going to be behind our factoring process here. Because see, if we're going to factor a cubic, we first need to find one rational root. And then when we divide it in by synthetic division, it creates a quadratic that we then know how to solve, right? Quadratics we could solve in our sleep, right? By factoring our quadratic formula. So that's what we need next. All right, let's bring this one down. Bring this one down here. Why don't you go ahead and do the synthetic division here. See what happens with this guy. So we have 2, -1, 2, -3. I'll let you go ahead and do it. All I really care about here is what happens down here. Did you get -27? Okay. So what does that mean about x plus 2? Not a factor, not a factor. And if I were to go f of -2, what should I get by the remainder theorem? You should get -27. Verify it. just going to take my word.
Yeah.
It does equal negative 27. So oftentimes all we care about is whether it equals 0 or not. Because all we care about is if f of negative 2 equals 0, then x plus 2 is a factor. If it doesn't, it's not. Okay, that's what we're testing. All right, factor theorem. A polynomial f of x has a factor, x minus c, if and only if f of c equals 0. That's what I just said. If we plug in negative 2 and we don't get 0, then x plus 2 is not a factor. If we do get 0, like we did here, so if I plug in 1 and we get 0, then x minus 1 is a factor. That's what that's saying. So let's see if you understand what this theorem is saying. This is a powerful theorem. It says, determine if x minus 1/3 is a factor of 3x cubed minus 10x squared minus 9x plus 4 without using synthetic division. How would you test to see if x minus 1/3 is a factor of this polynomial? What would you do? Pretend this is f of x. What is this saying here? It says a polynomial f of x has a factor x minus c, if and only if f of c, what's c in this case? Well, here's x minus c is the factor, so yeah, it's 1/3 equals 0. So what am I going to do here to test it? Plug it in, yeah. So f of 1/3, let's go ahead and do that, equals 3 1/3 cubed minus 10 1/3 squared minus 9 times 1/3 plus 4. So 1/27 times 3, I get 1/9 is what I got. Minus, this is 1/9 times 10, so 10/9. That's minus 3 plus 4. So 1/9 minus 10/9 is negative 9/9 or negative 1. Negative 1 minus 3 is negative 4, plus 4 is 0. So, to answer the question, yes, x minus 1/3 is a factor. An example of a rational root. All right. Number of zeros. A polynomial of degree n has at most n real zeros. This is kind of a softer version of the fundamental theorem. The fundamental theorem says, in terms of complex zeros, it will have n of them. Okay? In terms of complex zeros, it will have n of them. But this one's saying a polynomial of degree n has at most n real zeros. They could all be real, but they don't have to be. So the fundamental theorem says there are n complex zeros. This theorem is saying you could have up to n real. They could all be real, but they don't have to be. So when we're looking for real zeros, we know where the limit is. It's going to be whatever the degree of the polynomial is. That's as many as it could be. And the tricky thing is sometimes, as we saw last time, they come in multiplicities of more than one. So you could have 3 of them, and 2 are the same, and 1 is different. So there might only be 2 distinct roots. All right. Another theorem here. So rational zero theorem. It says if a polynomial has integer coefficients, then r over s is a possible zero. This symbol means such that. That symbol means such that r is a factor of the constant. S is a factor of the leading coefficient. I'll show you what I mean. This is what our learning target is today, is to use this idea to factor third degree and higher polynomials. It gives us the possible factors. So this theorem does. You may have seen this one last year. Okay. This is where we'll finish. So, the way to think about this is we're going to set up a ratio of all the positive and negative factors of R over S. Do you see what I said R was here? R is the constant, and S is the leading coefficient. Okay, so what we're going to do is create just a little ratio of all the factors of R over S. So what are all the factors of 4? Plus or minus 1, 2, and 4. Plus or minus 1, 2, and 4. And then all the factors of 2 are plus or minus 1 and 2. So what does that mean are the possibilities? Now, this is really powerful. What this is saying is that if there are rational zeros, okay, we're only talking about rational zeros, okay, which we're hoping there are some, because if this is third degree, actually we know if this is third degree, there's at least one zero in there that's not going to be complex, right? So we just want to find the rational zeros, and if there is one, it's going to be some combination of this stuff. Okay, so let's just write down all the possibilities here. So if I have 1 over 1, that would be positive 1, or we could also have negative 1. So we have, as opportunities here for zeros, we have 1, so let's just list them all out. Negative 1, positive 1. Okay, let's move over. What about the 1 over the 2, right? We could have positive 1/2, negative 1/2. And maybe it would be better if we, I want to actually list the specific ones. So negative 1/2, 1/2. Okay, you could use plus or minus signs if you want. Okay, so we did that with the 1. Now go to the 2. 2 over 1 is 2, so we have positive 2, negative 2. And then 2 over 2 is 1, and we already listed that one, right? Now let's go to the 4. 4 over 1 is 4, so we have positive 4, negative 4. And then 4 over 2 is 2, and we've already got that one covered. So if anything's going to work, it's going to be one of these numbers. So at least it's limited, right? We're not randomly going out and trying to divide different numbers into this polynomial. Okay. Then what the remainder theorem says is that you can quickly, even in your head in some cases, figure out if any of these are factors. And once you get one of them that works as a factor, then when you divide it into the third degree polynomial, what degree polynomial will you have? Second degree. Then it's no longer, you don't need to use the rational root theorem anymore. You could, but what you could do is take the quadratic and then factor it. And if it's not factorable, use the quadratic formula on it, and then you have all your zeros. Okay, that's the process. So, it still could be a lot of work. We have to just start plugging all these in. Okay, we're going to use them. We would plug them all in until we find one. And so, let's say, just say we started with negative 1. That's why I wrote this one first, because it doesn't work. Okay, but just yeah.
Is there a way to figure out what you should plug in besides just testing?
No, the rational root theorem just limits how many you have to test. There's no easy way. No. So there could be a lot of them, depending on what R and S are in this polynomial. But what I usually do just to, in terms of, is try the ones and negative ones, things that are easy to plug in that you can just plug in your head. Because as soon as you find 1, 0, that's all you need. Yeah, and then you don't have to use a rational root theorem on any others, because it's going to bring it down to second degree when you do synthetic degree. Yeah.
So you're trying to get it equal to 0?
You are. Yes. You're trying to see which one's easy. For example, if I plug in, let's just test f of negative 1. I don't want to have one that works on the first try, so I put negative 1 here first. So f of negative 1, when you plug that in, you get negative 2 plus 5 is 3, plus 11 is 14, plus 4 is 18. I get 18. So what does that mean about the factor x plus 1? Yeah, it's not a factor. It doesn't work. Yeah, whatever you want to say, right? So then I would go to the next one, which is going to work here. So f of 1, according to my notes, f of 1, I get 2 plus 5 is 7, minus 11 is negative 4, plus 4 is 0. So I had to think about this ahead of time. But what I don't want you to think is that it's necessarily easy. You could go through this whole list. It couldn't be till you get to negative 4 before one works. Because remember, there's only this is third degree, so yeah, one of these is going to work, but the other two could be complex, right? So you could go through the whole list, and don't get frustrated if you do. So a lot of times it's the ones and negative ones are a lot of problems here. So try those first. So what this means, let me just move this up right here. Whoops. Oh boy, now it's all completely separated. All right, but you get the point on that. Let me move this up. So that means if I, by synthetic division, if I do 1 here, let's bring it down 2, 5, negative 11, and 4. So bring down the 2. 1 times 2 is 2. 5 plus 2 is 7. Negative 4. 0. There's my 0 remainder. That corresponds to what I just saw when I plugged it in. So here's what this means. X minus 1 is a factor, right? Give myself a little more room here. So right here tells me that x minus 1 is a factor. So I could say 2x cubed plus 5x squared minus 11x plus 4 equals x minus 1. And then what do I have left over? This is where it gets a little easier. What does this mean? Remember? It goes down by 1. Okay, it goes down by 1 power, so it's 2x squared plus 7x minus 4. You with me? So now we've taken this cubic and made it into a factor times a quadratic. So now you could keep plugging in here. We've already tried these two. You could keep plugging in and see if you could find the other factors that way. They might be there, but there's no guarantee, right? It could be that the other two factors are complex. So the next question, what I would do on this, what I'm wanting you to do, is to go ahead and see if you can factor this. And if you can't, then use the quadratic formula on it. And that will tell you what the other roots are. So can we factor this? We already got it. Okay, so we have 2x and x, and it's saying we need to get an 8, positive 8, and a negative 1 there, and we're done. So that's it. Any questions on that? So the new thing is finding that one factor that's going to bring it down, or 2 if it's a quartic like my last one on there, to bring it down to something that you can then factor the rest of it. That's it. All right. So let's look at B. Let's make our little plus or minus thing here. Remember, this is R. It's R over S. I'm trying to think of how. It's last term over the first term's factors. You just got to remember that. Last term over first term. So, but last over first. So we've got plus or minus. Oh, that's nice. That's a 1. That makes things easy. It's really just the plus or minus factors of 21. So what are the plus or minus factors of 21? Okay, let's go. 1, 3, 7, 21. That's it. So I got to plug in those 8. And we're not going to start with 21. You can, but I would. So should we start with 1 or negative 1? What do you think? I won't look at it. I won't look at it. You don't start with 1? Okay, we'll see what happens here. So, okay. F of 1 equals, that's 1 plus 5 is 6. minus 17 is negative 11, minus 21 is negative 32. Rats. Anybody else have? So should we try f of negative 1 next, or has somebody already figured out what might work? I put mine down. I already had done it earlier, but I don't remember. What should we try next? Choose wisely, or we could be here. Should we try f of negative 1 next? Hey, what does f of negative 1 equal? You go ahead and tell me. Or verify with somebody. Now, this is bad if you make an arithmetic mistake, because then you could go through the rest of them. Actually, pretty sure. Do I have a verification of that? Anybody else think it's here? Okay, we got 2, 3. Okay.
I do too.
Okay. If it's not, it's going to really mess us up. So I hold you to this. Here we go. So what does that mean if f of negative 1 equals 0? F of negative 1 equals 0. Move all this over. It means f plus 1 is what? Now let's just erase this for now. Okay, so there's the last problem. We'll get rid of that guy. All right, so good. We tested it. That means x plus 1 is a factor. We're still going to have to do synthetic division because we need to know what quadratic is left over afterwards. So here's what I know so far. I've got x cubed plus 5x squared minus 17x minus 21 equals x plus 1 times something. Let's find that something using synthetic division. So I've got up here negative 1, and then we have 1, 5, negative 17. That's not enough room. This over. Okay, so we have negative 1 we're going to test. 1, 5, negative 17, negative 21. So it's 1, it's negative 1, that's 4, negative 4, negative 21, 21, and you guys are right. So here's what I have so far. I have, as factors of that polynomial f of x, x plus 1, opposite sign of that, and left over is x squared plus 4x minus 21. So is this factorable, the quadratic that's left over? So what are the factors? 7 and negative 3. Okay, so let's go ahead and finish it off then. With x plus 1, and you said x plus 7 and x minus 3. Let's just double check that. That's x squared. 7x minus 3x is 4x minus 21. Nice. We got it. That's it.
Ooh. Success.
That's it. No problem. Okay, it doesn't always go quite as cleanly as that, though. Let's try a 3C. All right, now remember, besides rational roots, we have rational numbers are also real numbers, right? They're not in the complex field yet. But besides rational roots, there's a bigger field outside of the rational roots. It's called the real numbers, right? The rationals are within the real numbers. Now, real numbers are ones where if you have radicals in them, but no i's, okay? Radicals, but no imaginary terms, no negatives under the radicals. So we have outside of the rationals, we could have answers that are real, and then we could even outside of that have answers that are complex, okay? But I believe this one is just real. There are going to be 4 real roots, but they're not all going to be rational. So here we go. Using our rational root theorem, we have plus or minus 1, 2, 3, 6 over plus or minus 1, 2, right? R over S. So let's go ahead and list all of our possibilities. So we could have plus or minus 1, plus or minus 1/2. Do you see where I'm getting these? So I'm putting the 1 over the 1, the 1 over the 2. Then I go to the 2. 2 over the 1 would give me plus or minus 2. 2 over 2 just repeats the plus or minus 1. Then we have 3 over 1. which is plus or minus 3, and then 3 over 2, which is plus or minus 3 over 2. And then move on to the 6. 6 over 1 is plus or minus 6. 6 over 2 is plus or minus 3, which we already have. Alright, so all of our possibilities. Right. We'll be here for a while, but not forever. Could be here for a while. Although, man, every time 1 or negative 1 is worth so. So what do you want to try first? Ryan wants to try 3 halves. Would you like to throw Ryan out of the...
Yeah, you should go and do it up there too.
Is he off the island?
No,
You already do. You should make Ryan do 3 halves first.
Yeah, you should do it in front of everyone else.
I didn't look. I don't remember what it is. So we're going to go with Ryan's 3 halves unless somebody...
I remember. No, I was kidding.
Make Ryan do the 3 halves, though. I don't...
Yeah, that's what I'm saying. Just make it.
What are the chances are we'll mess up the arithmetic on that? It could be a 0, it could not be. It won't matter because we probably won't do it right. So, all right. So let's try 1 and negative 1 first. We could probably handle those. So f of 1. I need some help here. And then f of negative 1. Let's break this up here. So f of 1 row. F of negative 1 row. And if we need to keep going, you guys are in the mix. So they're just going to keep sending in. It's like a war. If these 2 rows get taken out in battle, you guys are next in line. You don't like that analogy?
Makes you feel like
Yeah. Well, look at how far many rows back you guys are. That's the front line up there. You may end up trying 3 halves by the time we get here. Good. So f of 1 row. F of negative 1 row. Did you guys get?
It does not.
It doesn't work. What'd you get for f of negative 1?
I got negative 8. Yeah.
Did you both get negative 8? You're going. Man, I don't know, guys. Did you f of 1 row? You got 0? Get 0? Anybody else in the row get 0? You guys defeated the enemy in the first Tyler. Tyler just woke up. Tyler.
I think 1.
They're positive 1, yeah. Did you guys try positive 1?
2 plus 1 equals 3. Minus 17 equals negative 14.
Minus 4 is negative 18 plus 6. I get negative 8 for 1. Are you sure you got negative 8 for negative 1? So 2 minus 1 is 1. Minus 17 is minus 16. Plus 4 is minus 12. Boy, guys, I don't know. Plus 6, so I get negative 6.
Yeah, that's
Right over here.
I know. Okay, go to the next one.
okay.
What should we try next? Okay, this row right here.
Let's
2.
do
Okay, you guys got f of 2.
Alright.
And then the row next to it, do f of negative 2. Okay, you want to try f of 3. F of negative 3. We're going to make Ryan do 3 halves if we get that.
Yes. Yes.
I'll teach you to make any jokes in here. It's first period. It's too early in the morning for jokes.
Very true.
So I want to know numbers on this because I need 2 of you in the row to verify this. I can't. Negative 30. Negative. Okay. We got a not going to work for 2 people. Okay. Another line. Okay. F of negative 2. So F of negative 2 row.
We're still doing this?
Yes. This is how it goes. And
Dang. Come on, guys.
you're negative 2. It's you. You're speaking to yourself.
It's your turn.
Yeah, I did this last year.
Yeah, it doesn't care.
I already don't. I remember. Well, no, I understand this stuff. The next semester screwed me up.
F of negative 2 here. What do we get? 72. Okay. Oh boy.
Is it gonna be a half?
Wait, it's 6, remember?
Hmm?
Is it 6? I feel like I'm on.
Okay. F of 3. What's F of 3?
Can we use our calculator?
Yes, you can use your calculator. So I'm hearing from you guys that f of, I just forgot already. Would you say f of negative 3 were? and f of 1/2 gave us 0. Okay, that's nice, because if you just find one of them, it only drops it down to a third degree. So here, yes, it's good we found both. So here's what we have so far.
You need to use all of it?
Well, if you just stopped here, found this one, here's what we'd have. 2x to the 4th plus x to the 3rd minus 17x squared minus 4x plus 6 equals, so far we know it equals x plus 3 times something here. Right? X plus 3 times something. Now to find that something, it's going to be a cubic. We'd have to use synthetic division with -3. Okay, I know. We've already, but typically, what you would do on this is go until you find. You would go till you find the first one. I don't know that you necessarily that it's efficient to go through all of them to try to find the one or two that work. So you would go till you find one. Then what you would do is your synthetic division, which looks like this. So went through. I'm gonna erase this whole process. We found. Remember that 1/2 in there, but here we have -3, and let's go ahead and do our long division. 2, 1, -17, -4, and 6. So we got 2, that's -6, that's 15, that's -2, 6, that's 2, -6, that's 0. So I did my synthetic division, and that leaves me with 2x cubed minus 5x squared minus 2x plus 2. Now, fortunately, we already did the legwork. We know that 1/2 goes into this, right? So if I were to write this down again, I would say, okay, I know x plus 3 times, now I don't want to write it as x minus 1/2, though. I'm not going to write it as x minus 1/2. It's if x minus 1/2 equals 0, let's see, then, yeah, if I multiply through by 2 on each side, so I don't have any fractions, I have 2x minus 1 equals 0. And so that's my factor here. So it's telling me 2x minus 1. So if x minus 1/2 is a factor, 2x minus 1 is another way to write it. Okay, then, what's going to be left over? What's going to be left over here? So if x plus 3, 2x minus 1. Here's it. No, I'm not going to get it. I'm in the middle, mid dot here. I can wait. So we have 2x minus 1 is a factor. Another way to write it is x minus 1/2. When I do synthetic division, I've got to do it with 1/2. But I'm going to need to do synthetic division anyway, right? Because I need to know what this quadratic is that's left over. So I'm going to do 1/2. But I'm going to do synthetic division with just this guy right here that I'm circling. So you might want to make note of that. So do synthetic division with just the cubic that's left over, not the original 4th degree one. That's not going to help you. It's just going to give you a new cubic. Okay. So take the cubic and write down its coefficients. Okay, let me pause there so you can have a chance to write a note to yourself or something. It's this that goes in down here. The one that's been reduced down by 1 degree. Sorry. And I should have told you, don't write down like everything. There's certain parts of this you probably understood as to a, do it on the back. Do it on the back, it's fine. It's problem solving, basically.
I thought there was more on the back, just to see.
No, this is it, it's the last one. Okay, so bring this down, bring the 2 down. 1/2 of 2 is 1. That's -4. Half of -4 is -2. What's that? And then -4, and then half of -4 is -2, and then 0. So here's what I have left over. 2x squared minus 4x minus 4. Okay. So I'm getting this thing factored. I have 2 of the rational factors. Okay. Are you able to factor that quadratic? No, it's not factorable. It's not factorable.
I knew it. I knew you were going to
Not factorable.
The one with the most
So, but what?
was the quadratic.
Okay, but So, you know, we can use the quadratic form. We would, in terms of factored form, you could just leave it like this. You could actually pull a 2 out front. But if you're asked to find all the zeros, which I am asking you here to find, just find the real zeros and write in factored form. We got to do some more here. So, here we go. This is, let's bring the 2 out. Okay, bring the 2 out, x plus 3, 2x minus 1. And then if I bring that 2 out of here, I have x squared minus 2x minus 2. So you could use the quadratic formula to find the zeros. That would be fine. It might not be a bad idea on this, since we're going to leave it in factored form, to just do completing the square. But take set x squared minus 2x minus 2 equal to 0. And the advantage of complete, well, it doesn't really matter. You could use the quadratic formula. Let's do that here. That'd be fine. So we have x equals, opposite of b is 2 plus or minus square root of b squared, which is 4 minus 4 times a is 1, c is negative 2, all over 2 times 1. The advantage to using completing the square on this that I'm seeing is that you don't have to simplify the radical. So 2 plus or minus square root of 12 over 2. We can handle simplifying this, though. What comes out of this? Yeah, it could break down as root 4 times root 3 over 2. So x equals 2 plus or minus 2 root 3 over 2. I need to write down every step. I don't know where you're at on simplifying radicals. But greatest common factor, the factor that's the biggest perfect square, is 4. And so we have final answer, x equals 1 plus or minus root 3. So the zeros, let's list all the zeros here. The first 0 we found was negative 3, right? Second one was positive 1/2. And then we just found 2 more. They are 1 plus root 3 and 1 minus root 3. How do we go from zeros to factors? What do we do to go from zeros to factors? If I want to write all the factors of this polynomial, the factors are, well, let's write down the original polynomial again. It was 2x to the 4th plus x cubed minus 17x squared minus 14x plus 6 equals, so let's write down all of our factors. The first one was x plus 3, right? The next one was x minus 1/2, but we didn't write it that way. We wrote it as 2x minus 1. And then the next one was what was it? Well, we have these two, right? How do we write these as factors? Not sure.
I have no clue.
Okay, if this is the 0, 1 plus root 3, the factor is x minus 1 plus root 3. And we need to put it in parentheses. And then the last factor is x minus 1 minus root 3. Okay, that's a lot, yeah. So you could actually distribute this minus sign through if you wanted. I wrote it in this form. X plus 3, 2x minus 1, x minus 1 minus root 3, and x minus 1 plus root 3. Those are all the factors. Aside from, we also have that factor of 2 in there as well, but those are, I just sort of listed the factors.
there any of these, like, before anything we're going to be doing today?
There could be, yeah. There could be one.